I want to welcome everyone to the webinar here today. We're going to talk about actionable evapotranspiration data. And we'll talk quite a bit about the post-processing pipeline and some of the new features that we're going to have in the new LI-COR Cloud. For those of you that haven't seen the first of the webinars, we talked about the LI-710 evapotranspiration sensor, the Internet of the Environment, and the cloud. We had that webinar back in September of this year. If you haven't seen that, that's available on our website. This is sort of the follow-up part 2 to that. Go ahead. So I'm Dave Johnson. I'll be moderating today, handling the Q&A that comes in. I'd like to introduce our panelists. First, we have Gerardo Frattini. He's a principal scientist here at LI-COR and leads our ecosystem flux team. Comes from out of Italy and is known, most of you know him for his authorship and development of the EdiPro data processing software. He's been with LI-COR for 14 years. Next, we have Taylor Thomas. He's the product manager for our eddy covariance systems. And so he's working with researchers, helping to guide us and our instrumentation and software into the future. He's a panelist as well. And then we have Frank Griesbaum. Many of you know him. He works out of our German office and does a lot of support for the whole European Union and beyond. He's been with LI-COR for 13 years as well. And finally, I'd like to introduce the presenter today is Tyler Barker. He's a data scientist. He joined LI-COR not too long ago, but has a really very impressive skill set with a background in computer engineering. And so I'll go ahead and turn it over to him. Before we do that, on the next slide here, during the presentation, if you have questions and answers, make sure to click on the Q&A button at the bottom, not the chat. The Q&A will allow us to respond to questions in real time. We'll also pause potentially if we have some good questions throughout the presentation. So with that, I'll turn things over to Tyler.
Dave,
Yeah.
I covered the first few slides.
Let's turn things over to Gerardo.
Yeah, I will give just a little bit of an introduction before Tyler goes through the actual content of the webinar. So yeah, I'm Gerardo Frattini. Hi. So as Dave said, today we are talking about making evapotranspiration measurements, so ET for short, actionable, right? So for the sake of argument, we can think of ET in the context of irrigation, but the same problems and solutions apply in pretty much any domain where it is of concern. So I will shortly discuss the issue of estimating ET using models or directly measuring it. And Tyler will discuss what sort of problems, such as gaps and artifacts, measurements can be affected by, and which solutions LI-COR is offering to solve those problems and thus make those measurements actionable. So next slide. As you certainly all know, evapotranspiration is a key component of the water budget, of the water cycle. It consists of the water evaporated by the soil in the plants, as well as the water transpired by the plants. Despite its critical importance, however, traditionally, and still today for the most part, ET is not really measured, it is estimated, and almost universally by using model equations. Next slide. For example, one of these equations is a so-called reference ET, or ET0, which can be calculated using the Perman-Monteith model. There are other models, that's one of them. And if you look at the equation on the screen there are some variables and parameters there, right? So actually, even though you're using a model, you still have to measure something, right? You have to measure potentially the net radiation, the temperature, wind speed, even soil grounded flux, solid flux. And on top of that, next please. So on top of these measurements, you need to do quite a bit of modeling. So you see all these equations popping up on the screen. These are all the sub-modules of the model, that are necessary to estimate those parameters that get into the model. So this is just to show it's quite a bit of modeling, quite a bit of assumptions, and with that, quite a bit of uncertainty and lack of specificity. So now, despite being kind of an abstract general ET estimate, the ET0 is in fact used quite often directly to inform, for example, irrigation scheduling in agriculture. Now, next slide. So that's kind of, yeah, usually that's what people do. It can be refined. So ET0 is one estimate that can be refined into what is called actual ET, somewhat misleadingly, because it's not really an actual ET, it's kind of an approximation of the real ET. So how do we do that? We take the ET0, so the reference ET, and we apply a crop coefficient, so the KC in the equation, and that will give us the actual ET for our crop. Now, the crop coefficient itself is estimated from empirical relations from literature or from additional modeling. It is, as the name implied, is specific for each crop, but it's also specific for the growth stage of the crop. So it changes its value during the growing season. And again, this is just to show that you can go this route and you can keep adding pieces of modeling to estimate better and better the real life ET. Now, actually, actual ET should be really named potential actual ET if you want, because it estimates the amount of water that can be potentially lost by ET, by that crop, assuming, however, infinite water availability to the soil and the plants for them to evaporate and transpire. So both reference and actual ET, if you think about it, virtually by definition, are bound to overestimate the real actual evapotranspiration, right? So they can be further refined, and there are additional pieces of modeling, such as stress factors, for example, that can be added to further refine, but that's in practice not often done. So the question is, why don't we just measure ET, right? Well, it has been possible because of lack of technology, basically. But in fact, a methodology does exist that can do just that, and that's called ecovariance. Next slide. So LI-COR has been developing now for more than 30 years, I think, systems to measure directly the exchange of gases between ecosystems and atmosphere via the ecovariance method. So ET is nothing else than the exchange between ecosystem and atmosphere of the gas water, right? So we can apply the ecovariance technique to measure this quantity. So based on our decades-long experience, technological and methodological experience in ecovariance, last year we developed the LI-710 ET sensor. So that's a device that uses the ecovariance method to directly measure actual ET, right? Without the need of any assumptions, any parameterization or modeling whatsoever. What's more, ecovariance in general and LI-710 in particular measure ET at the relevant scale, so the field scale. So you can think of an ecovariance measurement as kind of an average of all the emissions of water across the field, as in the picture to the right, right? So it really measures directly the flux of water over the area of interest. Next slide. Okay, so now, actually, as Dave said, we have a whole webinar about the 710, so you can go look at that if you're interested. So now that we have a measuring device, how do the models compare to actual measurements? Well, unsurprisingly, for what I said before, the models tend to overestimate evapotranspiration. So in this plot, the red and green bars are measurements of ET by ecovariance on a daily basis. And the green one is the LI-710. And the gray and black are models, the gray being the reference ET that I discussed before, and the black being the potential ET, which I didn't discuss, but it's another way of estimating evapotranspiration. So as you can see from this plot right away, the estimates from the models are much higher than the measurements. And if you go to the next slide, you can see the accumulation of this data over time. And you can see even better how, well, first of all, how the true eddy covariance measurements kind of track each other so much that you can't even distinguish them in the plot. That is a kind of a quality evaluation of the LI-710 versus a traditional eddy covariance system. But more importantly, in this context, is you can see how the models overestimate the water loss quite significantly. So now, in the context of agriculture, overestimating water loss means overestimating irrigation demands, right? So that leads directly to water waste, additional unnecessary costs for energy, for example, and potentially even suboptimal crop yield. Okay, so so the value of correctly getting ET can hardly be overstated. Now, if you can go to the next slide. Now, like any other measurement, the LI-710 measurements are potentially affected by problems, right? Problems due to power shortages or malfunctioning, other, any sort of real life problems. In addition to that, the eddy covariance methodology requires atmospheric conditions that are not necessarily met all the time in the atmosphere. So this creates problems with our time series of ET. There are gaps, there are spikes, there are all sorts of, well, all sorts. There are some types of artifacts, potentially. Now, these need to be, first of all, detected and then eliminated so that the data can be kind of harmonized and consolidated into a data set that can be made actionable. So that's our task here. And that's the problem that Tyler will tackle in the remainder of the webinar, discussing what kind of problems can exist potentially and how our cloud software solves those problems. So I guess that's all for my introduction. So Tyler, I'll leave the rest to you.
Thank you, Gerardo. Yeah, so as Gerardo said, the evapotranspiration sensor here, the LI-710, we would like to have the data here in the left corner where it's all nice, continuous, and what we believe is indicative of what's actually going on in the field. But we may have particular power issues where the power goes down. There may be a gap in that data. We may have diagnostic issues or issues with the sensor itself that may cause the data to be considered bad or may cause the instrument to go down also. And then also just environmental issues. And so these would be rain, the sensor physically getting dirty, or any sort of conditions that we would consider to be we would consider that data to not be good. And so all of that really results in data having a very noisy, gaps filled, and lots of problems with the data that we would like to fix. And so, yeah, to reiterate, the challenge here is that the raw data must be cleaned, transformed into a continuous format, and also to ensure it's consistent in order to have these actionable insights or actionable choices to be made. And that process can be very labor intensive, time consuming, and also people may not be sure if they're doing it right. But we do need that accurate and reliable data is critical for making informed decisions such as irrigation in the field. And so what we like to talk about today would be a way to fix these issues with an actionable data processing pipeline. And so we want to implement this processing in post-field data to create a seamless, high-quality data set that allows experts to make these proactive decisions. And so this approach allows for more, could also allow for more advanced data processing, such as like ET forecasting, and also spatial processing on in a field of possible ET fluxes. And so first off, some of the data I'll show you in a second I'll talk about where this data came from. This data came from California in an alfalfa field, and it was actually sensed with 18 LI-710s. We'll only be analyzing the data from a single LI-710 for this purpose. So here's an example of the raw evapotranspiration data with gaps. And so we can see here that you can see where there's quite a few spikes in the data here, and that this can be caused by issues with how the data is processed in terms of the high frequency flux data, and mostly it's data that we would consider bad simply because those spikes are very large. And then also we see that we have a gap here in the data around a few days in. Each one of these loops here would represent 1 day. And so in this gap would cause issues if we don't do anything with it. May cause issues with us completely underestimating what the actual ET value is. But also if we gap fill it naively, it may not be representative of what's actually going on in the field. And so here we can see when we take this gap data in time series format on the top, and we do a daily accumulation of that ET values over a long period of time, we do see these effects of a gap happening. And also we see the effects of the spikes, but it's much harder to see in terms of the daily accumulations. But as we can see here, this may be affecting the data. And so what we receive in the accumulations, which would be a lot more actionable, it's a lot easier to look at, a lot more understandable to put it down to a single number. But what we see there is that it may not be indicative of what's going on in the field itself. And so here's another example of another post-processing step that we could do, which is the cumulative ET over this entire time interval. And so here we see that just from looking at it, we can't really see too much of a difference in this cumulative ET at that particular time where we see that large gap in the data. And here we definitely wouldn't see too many differences in terms of the spikes. But we still want the data to be consistent. We still want it to be as best as it can be to be able to make decisions on this data. And so what we look to do here, and this is just a quick example of the overall pipeline that we are looking here, and I'll go into more detail about how these processes exactly work in a minute. But we see the original data set at the top with all the spikes and the gap. And on the bottom, we see a preliminarily gap-filled data set with lots of these red points, which are defined outliers in the data. And so at this point, we would we're removing all of the spikes by a threshold detection algorithm. And then we are also identifying these outliers in the data to be possibly removed for future processing. And so this kind of shows what we can do when we're just looking at the data and knowing what time of day it is, and then using these algorithms that I'll get into in a second to get rid of these points that we would consider bad or consider not indicative of the sensed region. And then here is a final step that we would do once we remove these outliers and remove the properly gap the data set and remove any other data points that we consider to be bad. We can do a gap filling algorithm. And so the original data set is on the top, this raw ET values. And then on the bottom, we can see this clean data set. And it's much more well behaved. And it is what we would say would be actionable in terms of that we can then later do more processing on top of this and trust that what we're receiving is consistent with what we received before, but also something that is correct given the field that it's taking place in. And so here's another example of this when we can see the accumulations of the ET values per day on the bottom graph compared to the raw data set on the top. And this is the raw accumulations in blue, and then in light color blue, and then also in orange we see the filled data set for accumulations per day. And you can see that there is a very large difference in the two accumulation data sets at that day, where we see a large gap. And so we do see that what we have when we actually do these data processing is pretty important to how we interpret this ET values per day. If you only look at the raw accumulated values, you may not see. You may think that there's a more of a dynamic flow going on, and it could be the data could be giving you erroneous values. And also we can see on the other end over here where this corrected and clean data set in the filled continuous data set is actually under the ET value for compared to the raw data set. And so in this way, that was where the algorithms that we use to clean the data set have considered there to be a lot of points there that would either be spikes or outliers. And we can see that has a large effect on what is considered to be that ET value for the day. So from here, we can see that it's pretty important that we are doing this cleaning stages, and that we can do it in a way that is consistent and understandable. And finally, we can see the cumulative values for both the raw original dataset and the filled or gap filled dataset. And so what we see here is there is an important difference between the two curves that we see here, especially right where we have that gap. And so what we can see here is that, whereas before we couldn't really see a difference in this cumulative graph, now there is a very clear difference once we do all of these post-processing procedures. So that was to give a little bit of motivation as to why we are looking at these data processing procedures, and also what we expect to see at the end as to be this data as we would use as a data set for later data processing. And so I can pause the presentation here and to see if there's any questions that we would all like to answer before we get into a little bit more of the specifics of the algorithms used and the procedures used.
Okay. Yeah, we're getting quite a few questions in the Q&A and are answering them as we go. I think one of the questions that came up was asking about the sampling rate of the sensor, which I think we can answer that the LI-710 is sampling at 10 hertz or 10 samples per second, but the output from the sensor is every 30 minutes we get those flux values. Let me see. I think there was one question related to how is the gap filling done for missing data? What method will be followed? I wasn't sure if you had addressed that yet, Tyler, or if you plan to.
Yeah, I've not addressed that yet. That'll be later.
Okay. I mentioned that you will talk about it soon. So, and let me see. I think there was one other one. There was a question on the algorithms of removing spikes and outliers available, and what kind of method we use to gap fill the data. So again, I think those same types of questions, which you'll get to. So I think if you continue on,
okay,
we'll keep going, and we're answering questions as we go as well.
Okay, thank you. I'll continue on. So here's an overall overview of the data flow that we would be considering for this data pipeline. As Dave just mentioned, the actual data input to this procedure would be the 30-minute flux evapotranspiration values. So not the 10 hertz values, but these would already go through flux processing in order to get flex measurements at 30-minute values. And then we would go through a particular cleaning procedure. This is where we're removing any data that we consider to be bad, and also properly gapping the data. So any gaps that already exist in the data, we can see clearly. And so this would go through threshold filtering, diagnostic filtering, and a particular outlier detection, as we briefly mentioned before. And then from there, with that data, we can then gap fill it. And the gap filling algorithm we use is MDS, or marginal distribution sampling algorithm, which we'll talk about in a second. And then also from there, we would then calculate accumulations for a day or cumulative ET values for a time period. And then briefly, we'll talk about some more advanced data processing from there, which would be ability to do forecasting in the ET values, and also footprint or spatial modeling. So here's an example of the data that we received from the LI-710. In this case, this is ungapped data. And so we can see that there doesn't seem to be any real gaps in here, maybe one right here. But in terms of the data is not considered to be gapped yet in terms of figuring out where we're actually the instrument went down, or for some reason it's just not connected. And then also in this, we're also doing are able to do see the differences in location of this instrument. And so there's a GPS on board of the LI-710 apparatus and full system. And from there, we were able to see if there was any large changes in where the LI-710 was. And so we want to be able to do that so that we know of any other parameters that would change for the instrument in order to correctly analyze the data in this way. And so at the bottom here, we can see this red bars represent different portions of the data at different, which we have identified at different locations. And so here is a little bit more of the data scrubbing. So here's data that's already gone through the threshold filtering. In this case, the threshold is a simple cutoff of values that are considered to be not physically possible. And so in this case, I believe the cutoff was a negative 0.02 millimeters, and then 0.5 millimeters. And so on the upper end. And then we also go through a diagnostic filtering. This is based on a quality control check in the instrument. And so each one of the samples has could have a particular diagnostic code associated with it. And these samples are the 10 Hertz samples. And so if we see that there is a bad diagnostic code on a large portion of these samples in the instrument itself, we can flag that point as being poor quality or medium quality or good quality from that data set. And so we basically flag it in this case. I believe these are removed from this data set here. So here we can see that we're doing this threshold detection and then also a diagnostic filtering. We can see that there's large differences in location between basically the left side of this data set and the right side. And we can see that also from gapping in terms of time. Was a large amount of time in between here where the instrument was being moved that we don't necessarily want to analyze. So here's a zoomed in example of once we have the data filtered through a particular threshold, as we talked about before, and also a quality control step, we want to enter into an outlier detection. And so to first do this, we have to first fill the gaps in the data where they weren't already filled. But this is not the gap filling that we would want to end on, since this gap filling procedure doesn't really consider anything else about the environment or the instrument itself. And so in this case, we're just doing a preliminary gap filling, and in this case, we're using k-nearest neighbors prediction. And basically how that works is we're taking the time of day that the gap exists in, and then filling it with a statistical measure for an average, basically, for that time of day on a known ET sample. And so here we can see all the green dots down here. There's not too many in this data set, but all the green dots represents where we initially gap filled that data. This is important since in order to do this outlier detection, we do need a continuous data source first, and so we do need this preliminary gap filling. And so really all this is data that is filled in terms of the trend and its daily cycle throughout the weeks. And so it's a fairly simplified solution to this filling. And so here is the real algorithm for outlier detection, and this is from the paper you see on the bottom there. It's a agreed upon method for cleaning the data in terms of these outliers and also other quality measures in the data. And so what this does is that we can see the original time series at the top here. And it's about 2 weeks. And what we're doing is we're analyzing the trend, the season, and then the residual. And so the trend is basically a long-term trend in the data. It's basically what is the magnitude of the data as the time goes on. The seasonal component would be, in this case, daily cycles. And so we can see that in the season, these daily cycles as it's detected in the algorithm. And then what the residual component is if we subtract out this trend and the seasonal component from the original time series, we receive basically what the noise is in the signal, or deviations from this average of the season and the trend. And so what we can see there is that these points that I've identified with the blue marks here could be outliers in terms of the residual graph that we see here. But what we need to do is actually bin this data in terms of different times of the day. And then from there, we then fit a Laplace distribution over that time of day and find where outliers are in that Laplace distribution. And so this is a little bit more of an advanced way to find the outliers, other than a strict threshold of above this particular standard deviation, given the entire data set would be considered an outlier. But in this way, we're able to find, since we know that the data should be in a daily cycle every day, and we know particular things about the data, we should be able to have a more robust method for this outlier detection. And so as we can see here, so this would be the outcome given a larger data set of this outlier detection. And we can see all of these X points would be considered the outliers or spikes in this case. And so a few of these make sense in terms of the points. We see there's quite a few of them at the tops of the peaks here. And so those, visually speaking, look kind of like outliers. And so this intuitively makes sense. But there's quite a few points that in the lower parts of the curve that don't necessarily look like outliers. And this is from the fact that this is a fairly robust way to look at it. And so it may identify things that aren't visually obvious to be outliers. Now, just because we have identified these points does not mean that we will automatically remove them from the data set for future processing. What these points mean to us would be that this is just another evidence that the point is not necessarily indicative of what we want it to be. And so we would combine this with past information on the quality control of each of the data points in order to make kind of a final determination of do we want to get rid of these data points for future use too. We do this outlier detection would be considered a pretty conservative approach. It does flag quite a few more points than need be. but it does give us more information about how we can clean up the data set in this way. And so once we actually have clean this data set, we can then look to gap fill the data on a final gap fill. And so in this way, in this case, we would identify all the points that we would consider to be poor quality or bad. We would remove all of the points that we originally gap filled. And so all of those points go back to being gaps. And then once we removed all of those points, we then go in and gap fill. And so in this case, we're using the marginal distribution sampling algorithm that was originally proposed in this paper from 2005. And so this algorithm is considered to be a agreed upon academic algorithm for gap filling of flux values and ET flux values. And so what it does is that it combines the parameters around a singular ET value point, such as solar radiation, air temperature, and also vapor pressure deficit. And what it does is it finds patterns in those data and then basically averages over the known ET values around that data in order to fill the points that we're looking for in this data set. One important thing to also recognize is that if we focus more on the left side here, this would be considered to be a continuous data set on the left, where we're in a singular location for the instrument. What we want from the algorithm, the gap filling algorithm, is a continuous data source or a data set at the end. In order to do this, in order to get the best data at the end, we actually look for weather data given that particular location where the instrument may not have been working for that weather data. And so what we're looking for is to make sure that each data point is the best version of whatever that data point would be, but also make sure it's continuous. And so there's always a last resort data point that we'd be looking for in this set. So here's a similar graph with accumulation values per day. And so what we can see here is basically a guess for this instrument's detection of these ET values every day. And then we can compare this accumulation to the reference ET. This is from the FAO 56 model. And so it's less important here in this comparison to look at the absolute values, since the model is actually giving us a different ET measure that is not necessarily the same measure as the instrument, but they should be fairly consistent with each other in terms of not in terms of relative scales. And so, but what we can see here is that the measured ET values on the left, we can see a lot more dynamic results in how this accumulated values are being shown per day than in the reference ET. And so from here, we can see that you may actually be able to, if this data is from a week before, it will be a lot more useful to you in order to make assumptions or predictions off of this data than it would be to make over these other models that don't necessarily have exactly the same amount of information put into them, other than, or compared to what we can sense with the LI-710 and also through this data processing. So briefly, towards the end here, once we have this data in this gap filled set, we would like to also look at future processing in terms of forecasting these ET values. And we're still evaluating different procedures for exactly how to do this. But it's very important to us to have a good data set that we can either train off of for our models or use the data in the data set in order to predict future values in this forecasted data, either a day or a week ahead of time. And so you can see that the usefulness of this actionable data once we've gone through and cleaned the data set and processed it. And also, we would like to do more spatial data processing in terms of the footprint of the instrument, in terms of what we see with the flux values. And so here we see on this slide over here, here's a field with a footprint of the flux measurements, or of the predicted flux origination points given the particular instrument location of the LI-710 here. And so what this means is that given a particular wind speed, wind direction, we can see that the instrument is detecting flux from this particular area. And so from here, we will be able to have more advanced spatial processing as the wind changes, as the flux change, what we see in the flux changes. We will be able to create a much larger data set of how these changes do affect in that particular location, how these changes affect the spatial flux around the entire field. And from there, we can make maybe more informed decisions upon where there may be more water loss in one area of the field, and maybe where you're irrigating too much or too little. So, yeah. Okay. So that's pretty much the data pipeline that we presented today. And so we're looking for data that once we have cleaned it, once we have gap filled it, we're looking for data that we can act upon, and that people who know a lot about the field and know a lot about what their crops are doing, they can look at this data as one more point in order to make more informed decisions on irrigation or crop placement, or lots of different things that you could do in the field. So I will pass it back to Dave for any questions we have.
Yeah, thank you very much, Tyler. And for those in attendance, again, as we wrap up, go ahead and answer some, or enter some questions that you still have regarding anything you saw, either from the sensor itself, the measurements, or all the QA/QC and gap filling features that are going to be available in this LI-COR Cloud solution. I have 3 questions here that I'll ask the panelists. So maybe Frank, Gerardo, and Taylor, I have one for you each. If you guys want to turn on your camera and answer this, and I'll start with Taylor. There were quite a few questions about ecosystems that we've tested this in, how many years we tested it. I know we launched this product back in March 2023, so it's been in the field for a year, but can you give maybe some background information, what kind of sites this have used in, like crops or wetlands, that sort of thing, and maybe just some information on that, please.
Yeah, absolutely. Thanks, Dave. Yeah, so this sensor was released in early part of 2023, as Dave said, and prior to that, it was deployed in a wide range of different environmental conditions, so different temperature and relative humidity regimes, different climatic zones, not just in Nebraska or North America, but globally. Also was tested over both agricultural and natural ecosystems. So there's been some questions about, ET over forests or other natural ecosystems. The LI-710 has been deployed successfully in these types of conditions at a variety of measurement heights as well, and always benchmarking against traditional eddy covariance. So this would be a LI-COR LI-7500, 7200 gas analyzer, and ultrasonic anemometer. So using that as a reference system.
I would say a majority of the tests were performed in agricultural ecosystems because that is where there is the possibility to have a lot of management influence on the outcome of water use, water management more generally, and both specialty crops, places like California, as well as commodity crops throughout the US and globally. So a lot of different locations, and the theory and the practice of the sensor is broadly applicable to all of these different conditions.
Very good, thank you. Next question, maybe for Frank, if you're available. We had a couple questions related to using the 710 in colder climates, maybe over snow or something like that. Can you maybe talk about if that's a possible application? I know the sensor has some, I guess, specifications about when it makes sense to measure ET and when the sensor might shut down to prevent damage, that sort of thing. Can you elaborate on that, please?
Yeah, sure. So we like to prevent condensation inside the sample cell. That's why we also switch off the pump. So it's not sucking air anymore in. That is true for low temperature as well as very high relative humidity. Good to know is that very close to freezing conditions as well as very high relative humidity, there's typically very little evapotranspiration happening. By the way, there are more measurements than just evapotranspiration going on. There's also sensible heat flux that will move on down to -°C, which is also quite helpful to have in modeling aspects, for example. While the temperature is 5°C and the pump is switching off, that refers to the temperature inside the sample cell. However, the ambient temperature can be a little bit lower, close to freezing temperature, because the air is being warmed up, being pumped into the sample cell. And what the system is doing, it's switching on every 15 minutes or so. The pump sends the air temperature, then decides to continue or not. So under freezing conditions, as I said, and sublimation, I mean, that's relatively tiny fluxes, and the sensor hasn't been developed in the first place for that application. But someone maybe will get some sensible data, especially in the transition into from solid to melting phase. Some people were wondering to warm up actually the sample line, which is the lower arm of the analyzer, to push the border even harder. And I guess that's a kind of, I mean, we have seen this request quite a bit. So we may assume some people just get a unit or two, try it out, and maybe later on we can share you more experience how well that went.
Very good, thank you. Gerardo, I have a set of questions for you next. There were some questions about footprint and the area that these sensors can measure. Also related to that, I think was a little bit a few questions on the height of the sensor that we should put it up. So I know these all tie together, so maybe you can talk a little bit about footprints and how large, how small, where this can be used best.
Yeah, so first the easy questions. How high should you place the instrument? So the rules are the same that apply to any decoherence device. So there would be a very minimum height of 1.5 meters above the top of the canopy. That would be a kind of a minimum. You want to always be as high as you possibly can, with a limit that you don't want to have your footprint be too big, right? So try always to be that 1.5 meters, 2-3 meters high, I would say. Now the footprint, the LI-710 doesn't measure horizontal wind, as you can see from its geometry, right? So the instrument itself cannot estimate footprint directly. So the footprint image that Tyler showed there is derived in a somewhat different way in the cloud. So what we do is we use the data from the 710, and then we infer other inputs that are necessary for the footprint model, and we download data relevant to the site, so based on the GPS location for wind direction and wind speed, and using those parameters, which of course provide a more approximate footprint estimate than it would be done with a 3D sonic anemometer, right? We don't have all the measurements available, but nonetheless, we can compute the footprint that way. So it's going to be a bit more uncertain than traditionally it is, but it's still a good proxy. And with that, you can estimate how what is the highest height you can go. Typically, the footprint extends something like 100 times the canopy height above the canopy. So if you are 2 meters above the canopy, you can think of your footprint extending about 200 meters upwind.
Okay, thank you. Maybe I have one that came in that Tyler can elaborate on. So with the gap filling, there's drivers that are used, for example, air temperature and VPD, net radiation that might be on the station with the ET sensor. But if we assume the power went out and we don't have those biomet sensors available to use the drivers for the model, how do we handle that?
Sure. Yeah. So we do use weather data in that particular location of the sensor to get those values back for MDS. In that way, we still may have problems if that for some reason that data point doesn't have, or a set of data points does not have those drivers either. But then at that point we would do more advanced methods for either gap filling directly gap filling directly with just no data in terms of the MDS, or gap filling in some other way. But the goal is to have a continuous data set, and in times where we don't have weather data for the instrument and also don't have those that driver data for given the weather, it's probably would be good just to gap fill in the simplest way possible in either the MDS last ditch point basically, or either through doing a gap fill on those drivers itself and then doing the MDS. But yes, we will strive to always have a continuous data set.
Okay. And maybe Gerardo, if you're still available, put you on the spot once again. We've heard a couple times with people requesting ways to partition ET. Is that something that's possible to do with this, separating evaporation from transpiration, or heterogeneous, or is that something we think about in the future? Do you have any thoughts on that?
It's a good question. So the data, I mean, directly from the 710 cannot be used, standalone to partition into evaporation and transpiration. Additional data is required for that, some moisture and so forth is necessary. I don't know if this is something we haven't discussed this, I guess, enough to say this is something that's coming in the future. So I guess I'll leave it at that.
All right. Well, I think there are some questions still coming in, but we're at the hour mark here, so I wanted to thank everyone for attending, and feel free to contact us with further questions. There is going to be a recording of this video, so if you want to watch it later, you can go ahead and do that, or if you want to forward it to your colleagues. So I want to thank Tyler and Gerardo for their presentation today, and the panelists for answering the questions. And thank you, everyone, for spending some time with us today.